Hi, my name is John Fortner, and this is my report on Lab 2, Lines of Charge. Lab 2, Lines of Charge investigates how the observation of an object under the effect of zero net force can reveal information about the charge on that object. In this lab, we estimate the charge on two charge tapes. This lab relies on the momentum principle. By understanding that are floating charges under the effect of zero net force, we can calculate the electric force acting on the tape through Newton's third law. And then this lab also relies on the formula for electric field, which we use to estimate the charge on the objects of observation. The mass of one tape is 0.1968 times 10 to the negative 3 kilograms, or 0.1968 grams, and the distance between the tapes when one was floating above the other was 15 centimeters. The tapes are attracted to a negatively charged pen, indicating that they have a positive charge. So here we calculate the gravitational force acting on the tape, which is just the product of mass, the gravitational, or the acceleration due to gravity, and the direction y hat, and that gives us the vector negative 1.9306 times 10 to the negative 3 newtons in the y-hat direction. And then the electric force in the tape is just equal and opposite to that due to Newton's third law. So the same force but pointing in the positive y-hat direction rather than the negative. So at this point, Lab 2 starts to differ from Lab 1 in that we use a more sophisticated computational model to calculate a charge on each tape. So this model considers the tape as a line of 10 charges, with the charge on the tape evenly distributed across the line, as opposed to in Lab 1 when we just used 1 point charge as the estimate, as the model for the tape. So assumptions that we make are we ignore the impact of air resistance on the tape, and we assume that both tapes had about the same amount of charge. So here we can go ahead and run our model. So here you see these two tapes represented as lines of 10 charges. The red tape is our tape of interest, and the white arrow represents the electric force acting on the tape, and the yellow arrow represents the gravitational force acting on the tape, which, as you can see, had the same magnitude as was printed in the console. Then these green arrows on each of the red charges represents the net electric field acting on each of those charges. And then the total electric force is based on the sum of those electric fields added up according to the model. So we use the model to estimate the charge by manually inputting values until we obtain a charge that allows the model to satisfy the condition that the magnitude of the electric force is equal to the magnitude of the gravitational force. So from our model, we find that the charge Q is equal to 1.86 nanocoulombs. So we can go ahead and compare that with our results from Lab 1. So in Lab 1, we found that the charge on each tape was 6.94 nanocoulombs. So this indicates that we overestimated the charge on the tapes by roughly 400% in that original model. But our results weren't terribly inaccurate. We got the correct order of magnitude, and we used a much simpler model to do it. But our revised model in Lab 2 gives us a much greater degree of precision. So for the most part, our models in Lab 1 and Lab 2 are very similar, except that Lab 1 treats the tape as just 1 point charge, while Lab 2 uses calculus principles to divide the tape into a line represented by many smaller point charges. So in our case, we use 10 point charges to represent the line. And that makes the model from Lab 2 much more true to the actual observations, because our long tapes are much more similar to a line of point charges than they are to just one single point charge. Therefore, it stands to reason that the model in Lab 2 is much more accurate than that of Lab 1. That's all. Thank you for watching.